Dear students, in two separate lectures, I will talk about two important concepts when considering large projects: risk and safety. Risk and safety are quite familiar words, and because of that we need to define them precisely and consider them closely to make them useful to us. I am Frank Guldement and I work at the Safety and Security Science Group at the Faculty of Technology, Policy and Management here at Delft University of Technology. Next to some definitions, I will discuss in this lecture a few steps in a risk analysis. Let's start with some definitions. Our guiding questions for the moment are: what is risk? What is safety? And very briefly, what is security? We will not go into the latter concept in much detail, as it closely resembles safety for reasons that I'll explain soon. Risk can be defined as the probability of something happening multiplied by the cost or benefit if it does. Note that this definition is neutral with regard to the outcome of something happening. Please also note that risk is often used in relation to negative outcomes, outcomes that we want to avoid. We can put this definition into a simple formula, the so-called risk triplet. The risk triplet is the set of three questions that are used to define risk. The first question is: what can go wrong, represented by the S of scenario. The second question is: how likely is it, or the P of probability, and represented with the P of probability. And the third question: what are the consequences, represented by the C. I will come back to this triplet several times more during this lecture. There are, of course, different types of risks. And we can use two dimensions of risk, probability and consequence, to make some distinctions. So we have risks with a small probability and with small consequences. That means not many victims, like bee stings or being struck by lightning. We have risks with a large probability, but small consequences, like traffic accidents, various falls, for instance, from hate or smoking, etc. As you will have noticed, I've left out the third dimension of risk, the scenario. Many consequences can be caused in many different ways. It is therefore important that when we talk about a consequence, we also specify how this consequence could happen. Safety is defined as a state of being safe, free from hurt or injury. This is not an objective state, as people also need to feel safe. Because it is a state, the situation of feeling safe can change drastically from one moment to the next. As we also see, safety might conflict with other needs or interests, like economical ones. Safety has only meaning because there are threats. We will call these threats hazards. And they are defined as a situation that poses a level of threat to life, health, property, or the environment. Previously, we defined risk using the risk triplet of a scenario. What can go wrong? Probability, how likely is it? And consequences, what is the outcome? Hazards can also be seen as part of this triplet, the scenario and the consequence. Examples of hazards are driving a car, running a chemical plant or a nuclear reactor, or flying airplanes. The latter hazard is both for the people in the airplane and the people and assets on the ground. So, how about security? The difference between safety and security lies in the intention of acts. In case of safety, focus on plausible scenarios and a set of control measures. With security, however, focus on the intentional actions that can create large consequences. I will come back later to what scenarios actually are. One of the problems with risk quantifications is that they do not have a common denominator. This is important, otherwise we are comparing apples with bananas. So you will see risk quantifications in different guises, so be aware of that. If you want to compare risks of different activities, always make sure that you use the same measurement units. Here we have some numbers. I'm not sure what the numbers stand for, but I assume they express the overall probability that a person dies of this particular cause during his or her life. For instance, the probability of dying of smoking is 5 times 10 to the minus 3. So of 1,000 smokers, 5 die because of smoking. Dying in traffic is also possible with a certain probability, as is dying because of a stroke of lightning. Dying because of a chemical accident is the least probable. So let's add the probabilities of winning some kind of lottery to this table. As you can see, winning a lottery is not very probable. It is actually more probable that you die by the sting of a bee than winning the main prize in the state lottery. The question is often asked why we use people killed as the unit of measure. The reason is because people can agree on when somebody is dead and they have difficulty on levels of injury. Over the years, it has proven to be a good proxy for total damage, and several studies have shown this result. However, it is not a good proxy for disaster abatement, and where the numbers wounded and the extent of material damage are much more important parameters. We now turn to the topic of risk analysis. Of course, the main questions for a risk analysis are: what can go wrong and how? And this is our scenario. What is the likelihood of that happening, the probability? And finally, what can be the consequences? With regard to risk analysis, there are 2 approaches, the deterministic and the probabilistic approach. The deterministic approach is often limited to preventing the maximum credible accidents, like the exposure of a core of a nuclear reactor or a truck containing a hazardous chemical running into a building. Things we just don't want to happen, we prevent. In a probabilistic approach, we consider probabilities of particular accidents. I come to talk about this later group in my next lecture. A risk analysis is part of what is called a risk-based decision analysis. And it consists of 8 steps. In the first few steps, we define the context and the system we want to control for its hazards. And in the later steps, we actually carry out the risk analysis. Firstly, we define the context and the criteria for our risk analysis. Why do it in the first place? Maybe we're considering a new technology and we want to know whether it is acceptable. Or we have decided on a new technology, but we want to know where the risks are. And we also want to know who we need to involve, perhaps to control the risks, or to convince of the choice for the new technology. Whatever we do, we need to establish the criteria on which we base our decisions. This looks straightforward, but in practice it is quite complicated. In the Netherlands, and perhaps many other countries too, we make a distinction between internal and external safety. With internal safety, we basically mean occupational safety, the safety of people at the work in the plant or in the field. With external safety, we mean everything around the plant, the reactor, the activity. In these 2 lectures, we only focus on external safety. This is an arbitrary decision, as occupational is equally important, looking at the many occupational accidents we have each year. When we talk about external safety, there are different types of risks defined. We have individual risk, which was later replaced by localized risks. This is the probability that one person is being killed in a year at a particular place because of some hazardous activity. We also have group or societal risk, which is about a particular number of people being killed per year with a certain probability. And finally, we have the expectation value, which is an average of people killed per year. I'll explain the first 2 now. The probability that one person in one particular year is killed can be put on so-called risk contours. Those contours surround a potential hazardous place, for instance, a chemical plant or a nuclear power plant. At the points on this contour, all the points on this contour have the same probability. It is customary to draw these lines with negative exponentials of 10, like 10 to the minus 5, 10 to the minus 6, etc. I've drawn neat circles here, but in reality these contours can be very irregular. Group risk is usually represented by a graph, an FN curve, in which the frequency in years and the amount of fatalities is pictured. In this graph, we see a particular activity, for instance, the activity of one particular chemical installation and the frequency with which it will demand a certain amount of casualties. For this particular installation, the frequency is about once every 80,000 years, and we can expect 6 or 7 casualties. In the graph, 2 lines are also shown, which represent an agreement between parties, how much casualties and how often these are permitted. We can see that this installation is below this so-called norm. An interesting phenomenon can occur, which also makes clear that there is a tension between the concepts of localized risk and group risk. Let's assume the situation is like the one shown in this picture. Houses are built beyond the risk contour of 10 to the minus 6. So once every 10 million years, a certain amount of people might die because of a gas cloud, escaping this chemical plant. As you can see, the houses are built beyond the risk contour of 1 million years, so parties have agreed that this is an acceptable risk. The plant decides to take measures, making the plant even more safe. Because of these measures and agreements made based on the risk contours, houses can be built very close to the chemical plant. However, when a gas cloud now escapes, we have far more casualties. So localized risk and group risk can be at odds, and we have to agree at first on what we will focus. This is also shown on the next slide, where the yellow dot of the installation moves beyond the agreement lines. This is obviously an unacceptable risk based on group risk agreements. In the next 2 slides, I want to show that risk contours are theoretical concepts and accidents do not really pay attention to them. On October 4, 1992, an El Al Boeing crashed into an apartment building in the Bijlmer in Amsterdam. On the next slide, you can see its trajectory in red. The green contours are the low localized risk contours, the ones where you don't expect a fatality very often. As you can see, the Boeing crashed exactly in one such area. This finishes my first lecture on risk and safety and the first steps of a risk analysis process. Thank you for your attention.